Hello, everyone. In this video, we are going to discuss extreme values and saddle points of functions of several variables. Extreme values and saddle points of a function. Let us start with the following surface as the graph of a function of two variables. Suppose the function is continuous and differentiable at every point in its domain. Extreme values of a function refer to the highest point, the lowest point, in a portion of the surface, and the highest point, or the lowest point, in the entire surface. While a saddle point is either the highest or the lowest point in a portion of the surface depending on the direction at which the surface is traversed. In the following discussions, maximum and minimum values are collectively referred to as extrema, or an extremum. These extrema and saddle points exist at critical points or at boundary points in the domain of the function. This means that locating critical points and identifying boundary points are essential in determining the extrema and saddle points of a function. The function has to be continuous anywhere in the domain because we want to make sure that the absolute or relative extrema are indeed the extreme values of the function. Meanwhile, the function has to be differentiable anywhere in the domain so that we can identify the locations of all the relative extreme values of the function. Please watch at the end of this video for a review of sets which will be important in the next discussions about extreme values and saddle points. To be able to identify the extreme values and saddle points of a function, we first need to locate its critical points. A critical point can be any point in the domain such that at least one neighborhood containing the critical point is inside the domain. That is, it is an interior point of the domain. Every interior point of the domain can be a critical point, but we will narrow down its location by imposing conditions on the function. A critical point may be stationary or non-stationary depending on whether or not it satisfies a couple of conditions. Stationary point. A stationary point is a critical point where both first-order partial derivatives at that point exist. This means that the function is differentiable at a stationary point. In addition, these first-order partial derivatives must be both equal to 0. This means that the slope of the surface in the x direction and the slope of the surface in the y direction are both 0 at these points. Recall that for a function of two variables, differentiability means that there is a non-vertical tangent plane to the surface at that point. Non-vertical means either horizontal or sloped. The first-order partial derivatives are 0, so it specifically implies that the tangent plane to the surface is a horizontal plane. Non-stationary point. Please consider the following graph of a function of two variables. A non-stationary point is a critical point where one or both first-order partial derivatives at that point does not exist. This means that the function is not differentiable at a non-stationary point. For a function of two variables, its geometric interpretation is that there is a vertical tangent plane to the surface at that point. These are the first-order partial derivatives of the function. The value of the function is assigned as the dependent variable, so these partial derivatives can be expressed in terms of the dependent variable. Each partial derivative does not exist if the denominator is 0. This happens if the point in the domain is in the following set, which corresponds to a circle in the xy plane. Suppose we focus on one of these points. The partial derivatives at this point are given by these values, where c is equal to 0. Substitute these values into the equation of a tangent plane to the surface. After multiplying both sides by c, and then letting c be equal to 0, it simplifies to the following equation of the vertical tangent plane to the surface. As another example, please consider the following graph of a function of two variables. These are the first-order partial derivatives of the function. The value of the function is assigned as the dependent variable, so these partial derivatives can be expressed in terms of the dependent variable. Each partial derivative does not exist if the denominator is 0. It is satisfied if the point in the domain is in the following set, which only happens at this point at the origin. The partial derivatives at this point are given by these values, where c is equal to 0. Substitute these values into the equation of a tangent plane to the surface. After multiplying both sides by c, and then letting it be equal to 0, the equation simplifies to just an identity. Hence, there is no tangent plane to the surface at the point. Boundary points. Extreme values and saddle points can also be located at boundary points of the domain of a function. Please consider the following graphs of functions of two variables. The highlighted part of the xy plane refers to the domain of the function. In the first graph, the function achieves the absolute maximum at a boundary point. Meanwhile, the function attains the absolute minimum at a set of boundary points. In the second graph, the absolute maximum is achieved at a boundary point, while the absolute minimum is attained at another boundary point. Relative maximum and relative minimum. A relative extremum is the extreme value of a function on a neighborhood of a critical point. A relative maximum is the highest value of a function for all points near a critical point. Meanwhile, a relative minimum is the lowest value of a function for all points near a critical point. Note that a relative extremum can only be located at a critical point, but not at a boundary point because a critical point has to be inside a neighborhood, as mentioned earlier. It is easy to identify a relative extremum using graphs. But in the next pages, we will introduce a couple of tests to identify a relative extremum. As mentioned earlier, a relative extremum is located at a critical point where the function is differentiable, and therefore continuous. Let us show another illustration involving relative extrema. Consider this graph of a function of two variables, which is defined on the entire real plane. These are the critical points of the function. These are points in the domain of the function where the partial derivatives of the function are 0. The highest point in the surface on a neighborhood of a critical point is a relative maximum. And this is the corresponding value of the function. While the lowest point in the surface on a neighborhood of a critical point is a relative minimum. And this is the corresponding value of the function. First derivative test. This test confirms that a relative extremum at a point satisfies these two equations for stationarity. That is, if there is a relative extremum at a point, then that point is a stationary critical point of the function. These two equations can be combined into a single vector equation, which means that at a relative extremum, aside from seating at a stationary critical point, the gradient of the function at that point is the zero vector. However, if the gradient of a function at a point is the zero vector, it is not guaranteed that there is a relative extremum at that point because there may be a saddle point instead, which is not a maximum nor a minimum but is located at a critical point. In summary, a relative extremum sits at a stationary critical point where the gradient of the function is the zero vector. But a zero gradient does not automatically translate to a relative extremum. Now let us revisit an illustration we had earlier. The first derivative test says that a relative extremum satisfies these two equations. This test also tells us that a relative extremum is located as a stationary critical point of the function. Let us confirm by computing the first-order partial derivatives at each point. This is the partial derivative of the function with respect to x. And this is the partial derivative of the function with respect to y. Substitute each point into the partial derivatives. So each relative extremum satisfies the two equations above, and that these points in the domain are critical points of the function. Second derivative test. This test aims to classify a stationary critical point as either a relative maximum, a relative minimum, or a saddle point. It is difficult to use these inequalities to test every point near a critical point. So use this equation containing second-order partial derivatives to classify a critical point. If d is greater than 0, and this second-order partial derivative at the point is less than 0, then the extremum is a relative maximum. If d is greater than 0, and this second-order partial derivative at the point is greater than 0, then the extremum is a relative minimum. However, if d is less than 0, then there is a saddle point at the critical point. If d is equal to 0, then the test is inconclusive. Remember that this test has a similarity to the concavity test we studied in Calculus 1. Let us revisit an example earlier. This is the first-order partial derivative with respect to x. And this is the first-order partial derivative with respect to y. Then find the second-order partial derivative with respect to x, and the second-order partial derivative with respect to y. Next, determine the second-order mixed partial derivative. Note that the discriminant is computed from this partial derivatives. The second derivative test tells us that if the discriminant is positive, then there may be a relative maximum or a relative minimum at a critical point. Substitute each critical point into the partial derivatives and compute the discriminant. The critical point on the left has a positive discriminant and a positive second-order partial derivative, so the function has a relative minimum. The critical point at the center has a positive discriminant and a negative second-order partial derivative, so the function reaches a relative maximum. And the critical point on the right has a positive discriminant and a positive second-order partial derivative, so the function achieves a relative minimum. Here is a quick review about sets. A set is a collection of points. In n dimensions, a point represents an ordered n tuple, or an ordered sequence of n real numbers. Consider these four other sets of n-dimensional real numbers. The first and second sets contain points that satisfy a given condition. The third set is the set of all points in an n-dimensional space, while the fourth set is the set of all points in an n-dimensional space with non-negative coordinates. These regions contain the interior points of the set. An interior point is a point in a set where at least one neighborhood containing the point lies inside the set. An exterior point is a point where at least one neighborhood containing the point lies outside the set. And a boundary point is a point in a set where every neighborhood containing the point has points inside and outside the set. Based on these definitions of points in a set, let us define the types of sets. A closed set means all boundary points are included in the set. Meanwhile, an open set means all boundary points are excluded from the set. In writing, if A and B refer to boundary points, then an equality denotes the inclusion of these points in the set. The second set explicitly tells the boundary points and both are included in the set, while the fourth set implies the coordinates of the boundary points included in the set. In illustrations, solid lines mean the boundary points are included in the set, while broken lines mean the boundary points are not included in the set. Next, a bounded set means the set can be contained in a larger finite closed set. Otherwise, it is an unbounded set. The two sets above are bounded because they can be subsets of a larger finite set, such as a set with larger distance between boundary points. However, the two sets below are unbounded because both have infinite number of points, and therefore cannot be contained by a larger finite set. Please watch the next video about saddle points, absolute extrema, and extreme value theorem. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.